E-bit.
We are the generation.
We are the problem solvers.
We are the innovators. We change the world.
We keep reinventing ourselves
To remain relevant
And compete globally.
Creating a peaceful and sustainable planet for all humans.
That is why we start today, innovating our tomorrow.
Welcome to Engineering 4.0.
The state-of-the-art Engineering 4.0 facility is positioning the University of Pretoria as a center of excellence in smart transportation and structural engineering. This unique world-class African facility is situated in Hillcrest on the Innovation Africa campus and in close proximity to the university's Future Africa complex, a hub for inter- and transdisciplinary research networks within the University of Pretoria and the global research community. It houses state-of-the-art laboratories and training facilities, including the York Wood Engineering Laboratory, in partnership with York Timbers. This laboratory endeavors to cultivate, grow and expand the footprint of mass timber construction using advanced engineered wood products in South Africa and on the African continent, in a collaborative effort between civil and chemical engineering, architecture, genetics and other related wood bioeconomy disciplines. The research done at Engineering 4.0 will contribute to a more sustainable and prosperous future for the citizens of the country and African continent.
Join the revolution of open source software at the freecad and CAE Users Conference. Hosted by the University of Pretoria and powered by the Royal Academy of Engineering and Engineering X. From March 1st to 3rd, come together with a community of creators and users on the Hop-In platform to share knowledge, network, and learn about the latest developments in the world of freecad and CAE. It's a great opportunity to learn from experts in the field, network with like-minded individuals, and stay up to date on the latest developments in the world of open source software. The conference aims to bring the world of open source software closer to the public and showcase the potential of freecad and CAE through presentations, workshops, and interactive sessions. Attendees will have the opportunity to learn from experienced users and developers as they share their knowledge and experiences with the software.
Open source software, such as freecad, is changing the way we think about and use technology. Open source software offers collaboration, accessibility and innovation. In the field of AI, it leads to faster and more efficient development through collective work and sharing of knowledge. It helps democratize technology and make it accessible to more people.
The conference will take place on Hop-In, a virtual event platform that allows for live streaming, interactive sessions, and networking opportunities. Together, let's embrace the power of open source software and shape a more inclusive and innovative future.
The freecad and CAE Users Conference, where creativity knows no bounds and distance is no barrier.
So I guess it's my turn to welcome you to this freecad Users Conference. I'd like to first thank everybody who organized this conference, Varnu and the University of Pretoria to host it. I will talk briefly about the state of affairs of freecad, where we stand, where we're coming from, and where we are going. So I'm Jorik, I'm one of the main freecad developers. I'm also the president of the Freecad Projects Association, the new non-profit body we have developed around freecad. I'm an architect by trade. I do architect work, I do programming, I do 3D rendering, urban sketching, comics writing sometimes, etc. So I would begin with a quick history of freecad. Freecad, the development began around 2002. It was a two-person affair that started in Germany, basically, when Open Cascade, which is the main component of freecad, got open sourced. Open Cascade is a gigantic geometry modeling kernel and it has hundreds and thousands of functions and tools for doing anything related to geometry, manipulating solids, NURBS geometry, etc. And it's basically the basic building block of FreeCAD. Without it, probably FreeCAD wouldn't be there, because programming a geometry kernel from scratch would be close to impossible mission. So the project grew steadily, with 2 persons working on it for years. In 2008 I joined the project. So it became a 3-people project. Basically I was in search of a way to do architectural work that wouldn't depend on the big software vendors, because I was working in a small office, and buying software license for both of us would have been like hiring another person, so it felt like impossible. So I began to search for free and open source solutions, and I stumbled upon FreeCAD, who was basically not much more than just a 3D platform with a big Python interface, and I thought, okay, that I could maybe help and do something. So during these years, a couple of other developers joined. In 2010 we have the big 3D printing boom. You begin to have 3D printers everywhere. Fab labs began to appear and to develop, and that's basically where FreeCAD began to be used a lot. And so the number of users and developers began to grow a lot. In 2020, Fusion 360 products by Autodesk began to put a lot of limitations to the users. You couldn't export your work anymore, and anything a bit more than basic that you wanted to do you would need to buy a license. So a lot of users of that product began to search for an alternative, and we had a big spike of users coming all at once in FreeCAD. With that came more interest in the media, etc., etc., and we had another expansion boom happening. And today, basically, FreeCAD has more or less 30 regular developers. I mean, people who contribute, let's say, once a week at least, or a couple of times a month. We have a non-profit body that I will talk about next. We begin to have funded development opportunities, like people can begin to work on FreeCAD and earn money for it, and FreeCAD is entering the corporate world. You begin to see companies beginning to use FreeCAD for internally for their work, and begin to look at it and involve themselves with FreeCAD. The non-profit body of FreeCAD is the FPA. We call it the FPA. It's the FreeCAD Project Association. It's a non-profit association that's built to support the FreeCAD community. It's not built to rule over FreeCAD. It's built to be a kind of side project to FreeCAD, or let's say a tool for the FreeCAD community. Basically what it does is gathering funds from donators. Lots of people and more companies want to help the FreeCAD project, but they cannot code, or they cannot put time into it, and they would like to support the project with money. So basically that's what this association is there for, to be a place where they can donate money, and it redirects that money to different kinds of uses and projects around freecad. So it organizes projects to use that money for example, to develop some parts of freecad, etc. It supports the developers, it helps the developer to do their job better, for example, paying for their time. And another important use of the non-profit is that it helps to protect the community-developed model of freecad. The community, I talk a lot about the freecad community because freecad is essentially a community project. It's more like the original freecad developer Jürgen said once, freecad is much more a social project than a technical project. Everything is made by the community in freecad. There is no boss. The community decides, the community organizes, the community put things in place to make things happen. The community writes documentations, translations, and everything in freecad. And the community is made of developers, users, companies more and more, but basically users. Most big part of the freecad developers today are users who learned to code. And freecad is essentially a project developed by its users. The community also, each person who contributes to the code of freecad has ownership and copyright over that code. So the whole freecad code is actually owned by a lot of people, more than 200. And this is something that gives strength to freecad. You cannot buy something from 200 owners. It's basically impossible. And the community is constantly creating side projects, and so the whole ecosystem of freecad is growing and spreading a lot beyond its limits. A quick note about open source development model, which is the model of development of freecad. Basically, the basic assumption is that it's your software. You take it, you take the code, you take the software, and it's yours. There is no contract between developers and you, the user. You take the software, and its license is actually there to protect your rights instead of limiting what you can do with the software. Another very important point too is that the data you produce with the software, the models you produce with freecad, are also entirely yours, not only by license, but also the way the data is formatted. FreeCAD files, FreeCAD models can be opened without FreeCAD. Basically the FreeCAD file is a zip. You can unzip it and take the component inside it. Most of things are text-based files, and it's all open formats. So you could open a FreeCAD file in 50 years from now without FreeCAD, with another software. It's your data, and it's designed to stay that way and to be accessible to you, so that you won't lose any data over time, even if FreeCAD would disappear someday. Lots of people think open source development is bad quality development, and we used to say it's actually the contrary. The way FreeCAD is developed, the way features are validated, are checked, are analyzed by other people, the way bugs are always kept somewhere until they are solved, the way the code is checked for error, etc. All of these are methods, are very professional methods. The development methods of FreeCAD, the way FreeCAD is developed, being open source, is highly professional. I dare to say more professional than inside many software companies. FreeCAD also has a very large development team. It's not three people, it's hundreds of people who are developing code, who are testing code, who are suggesting changes, who are finding bugs, and who are documenting how the different features of FreeCAD work. There are not many software companies in the world who can gather such a team on a single project. All this gives actually a very high quality level of the FreeCAD code. And we also have several perks at FreeCAD, things that you wouldn't find so easily in commercial applications. Every file that FreeCAD reads and produces usually follows open format specifications. FreeCAD works a lot with open file formats. I say usually because it still can import a couple of proprietary file formats. But everything you produce with FreeCAD is open format. It can be read with other applications easily. It can be exported and easily imported in other applications. It can be opened and read with a text editor, things like that. Often in commercial software, compatibility is actually restricted. They want to keep their users into their own solution. In FreeCAD, we don't have this commercial interest. We like compatibility, and we want compatibility with anything possible to happen. So, for example, FreeCAD exports and imports around 50 different file formats, and there are much more that can be plugged in, and so it's a lot of different file formats. We have backwards compatibility. That's kind of expected. And in FreeCAD, we also have something else that is forward compatibility. That's something you won't find so easily in commercial applications. That means that a file produced with a newer FreeCAD version can still be opened with an older FreeCAD version. So you could open a file produced today in a FreeCAD version of 5 years ago. And that is because they all follow the same structure. The file format is incremental. So only the new items that didn't exist in the 5 years ago version won't be there, but the file can still be read. And there is something fantastic when you work with FreeCAD and when you work on developing FreeCAD, is that you work with no deadlines, no pressure, no boss. Nobody who tells you how you must work. You decide how you best do your work, and you discuss with others if your work is overlapping or stepping or intersecting with the work of others. That's just a normal way to do things, but you decide on your own stuff, and that's something that's really a nice work environment to work with. So to talk a little bit about FreeCAD itself, the main feature of FreeCAD is parametric modeling software. Parametric modeling basically means that the FreeCAD objects are like little programs which are run every time you need to recalculate the shape of that object. So for a box, for example, will be defined by length, width, and height. And every time you change one of those parameters, the program runs and recomputes the shape of the box based on these three parameters. And parameters can be anything, can be pieces of text, numbers, or even be something from another object, like a face of another object, or the length of another object, or something like that. So you can really begin to think of big parametric chains, where one object, like you have a line, and the length of the line drives something else, the whole shape or the position of other objects, or how big they are, or things like that. and you can have a couple of master objects who drive all the rest of your objects. The other advantage is that these parameter changes are easy to record. So if you change the length of your box from 2 millimeters to 10 millimeters, that's a very simple operation to record. That also means they can be easily undone. You set the parameter back to 2 millimeters and the shape is recomputed back to when it has 2 millimeters. FreeCAD is also a generic modeler, and that's also an important thing. At the base is just geometry engine, a big geometry engine that supports solids and NURBS geometry. You can do solids, NURBS surfaces, NURBS curves, line work, meshes, annotations, text, dimensions, and bring into this a lot of other kinds types of objects. So FreeCAD is really a very generic toolbox for geometry modeling. It has no specialty. All the specialties, for example, we have workbench to do woodworking, to do sheet metal folding, to do architecture and BIM, to do boat hull design, and those are all plugins around the core applications. The design of FreeCAD itself, how the code is designed, is very modular. The engine and the interface codes are separated. The code is carefully separated into different sections. There are boundaries between these sections. There are dependency. One part can depend on another, but the other cannot depend back on the first one, so you have a clean dependency tree. And mostly everything in FreeCAD is a plugin. You have a very small core that doesn't do anything, basically. Just opens a 3D window and allows to save and open files, and that's it. And everything else is actually a plugin. So you can have many developers working together, each one on their own parts of the code without interfering with the others. You have a quite low entry barrier. That means that someone new to FreeCAD and to coding can start by learning just a little bit, a specific part of the code and grow their knowledge from there. And we have, thanks to that, a quite easy merging workflow where lots of different code change and contributions can be merged together without interfering each other. Another interesting feature of FreeCAD is that it has Python everywhere. Python is a very human-oriented programming language. It's really, really easy to learn, and that's a very important feature of a programming language too. It attracts a lot of users. Users can easily begin to code in Python, etc. In FreeCAD, the most of the core functionality is coded in C++, which is a much more efficient language. So everywhere we need efficiency and speed, it's coded in C++. But most of the outer layers that define the tools themselves, the interface, how things work for the user, are coded in Python. And also, that's an important point, all the glue between the core application and the interface is coded in Python. That means every time you press a button in FreeCAD, you're actually executing one line of Python code that goes to the core and that tells it what it has to do. And there are lots of easy and didactic tools in FreeCAD, like you have a window that you can keep open at the bottom of your screen, where every time you click a button and that line of Python code is executed, you see it in that window at the bottom of your screen. So you end up learning how FreeCAD works. You see that line of code and you could copy it and change it and make it happen yourself and put it in a script, and that's it. You're beginning to code for FreeCAD, and that's actually how many of the FreeCAD developers began to code, just by tweaking with this Python code there. So I'd like to finish by talking a little bit about what I personally am doing with FreeCAD. Basically, my area of actuation in FreeCAD is mostly centered around BIM, which are tools for architect, engineering, and the construction field. Do a very quick history of where we're coming from. Basically, up to today, actually, most of the work done in architecture, engineering, construction field is still done with 2D drawings. That comes from the time where you would draw directly on big sheets of papers and give this sheet of paper to people on the work site to build the building. In the 80s, we began to have the first 2D CAD systems, basically AutoCAD, which was and still is the main player in that field. Then these platforms began to gain 3D capacities, and finally we are now arriving at something they called BIM. BIM stands for Building Information Modeling. It's basically CAD for architecture, engineering, construction. Basically, BIM models are 3D models with more non-geometrical information in it. If you think that a drawing, which is still needed at the end, because what goes to the work site, what carries the information, what gives the information to people who actually build the building, still goes through drawings. They take the drawings, they look at drawings, and they build according to the drawings. It's still something made by persons, by humans, and so drawings are still the way we communicate to those people what needs to be built. A drawing is about 50% geometry and 50% annotations. This is size of thing, this is size of that, this is made of that material, this should go before that. That kind of information, which is not just lines and geometry. And the BIM model basically holds everything, or that's the idea, it's to hold everything inside the model that you would need to produce those drawings. So you would have like one model and you could extract those drawings automatically from it. So how is the BIM situation today? Now basically we have two companies owning almost 100% of the BIM software used in the world, in architecture and engineering offices. So this is a worrying situation. You have both of these enforce closed ecosystems where they try to maintain their users hooked to their own solutions or a panel of solutions. And they are big companies driven by commercial interests. So the tools you use as a professional, as an architect, as an engineer, are actually decided. How those tools work are decided by a commercial team, basically. And that's something pretty worrying, that architecture especially is still a very, there is a artisanal aspect of it, that you as an architect are a crafter. You model things, you decide how you model things, the same way as a lumberjack would be the best person to define how wood axe should be, how it should be shaped, where the weight should be, etc. So you as an architect should be the main person to decide how your modeling tools should be. And that's not what's happening with BIM software today. And even more worrying, you begin to see that this software, a simple Google search would confirm that to you. And all those models, that architecture produced with those software begin to look alike. So it begins to influence the way we do architecture, because the restricted set of tools force all users to go along the same ways and to adopt the same solutions. And that's definitely something where open source software can change things and make a big difference. In open source BIM, we already have several working solutions, solid working solutions. FreeCAD is one. You can already do complete BIM projects within FreeCAD. Blender BIM is another. IFC OpenShell is another piece of solid software that is used in an open source BIM ecosystem. IFC.js. There are many others. All of these pieces of software have very high interoperability, and they all communicate extremely well through each other. Most of the time because they use the same components, they have the same basis, but also because they use the same formats, and more even simpler than that, they want to interoperate. You have many specialties. You have software for modeling, for analyzing, for producing, all kinds of byproducts you need around. And there is one big file format used everywhere there, which is the IFC file format. The IFC file format is an open standard. It's managed by a consortium. It's extremely well documented. All the specification of what's inside that file format, how it must be formatted, is open sourced. It's well explained how you must compose your file, etc. And the IFC format itself is a text format. If you don't have any BIM application to open an IFC file, you could open it with a text editor, and you could read the lines inside and understand what's going on. You could very easily make a little program to extract the information that you need from inside an IFC file. It can even be rendered in a spreadsheet form, so you can look at an IFC building in a spreadsheet application. Have the quantities of doors, have the quantities of walls, etc., etc. And this is what I'm currently developing in FreeCAD. It's native IFC. The concept native IFC means being able to open and save IFC files in FreeCAD natively. That means without having to convert the data to FreeCAD internal model, to FreeCAD internal data structure, and then convert it back to EFC, because all these conversions make you lose pieces of data or even reorganize pieces of data. And so the idea is really work with the IFC data itself inside FreeCAD. That is already working in Blender BIM. Blender BIM uses native IFC concept already very successfully. So that means in FreeCAD basically that we don't use Open Cascade directly anymore. We use another geometry engine, which is IFC OpenShell, which is what produced the geometry you see in FreeCAD. So all the geometry you see and you manipulate in FreeCAD is always produced directly from the IFC file. So you change something in the IFC file, the geometry you see in FreeCAD is updated. And there are very interesting consequences to this, is that if you change one thing, the name of an object in FreeCAD, there is one place in the IFC file where it has changed. So this makes it very very friendly to version control. Version control system can give you two versions of an IFC file and show you where things have changed. So basically that's it. Thank you for watching. Here are a couple of links where you can reach me, or just Google me and you find more. Thank you and enjoy the rest of this event.
Hello everyone, my name is Oliver Oxtoby and I'm one of the developers of the CFD-OF workbench for FreeCAD. So CFD-OF is a workbench for fluid flow simulation using the OpenFOAM solver, which is perhaps the best known open source CFD solver with quite some industrial pedigree. But it does come with the reputation for having a very steep learning curve. And you can see on the right an example of one of the input files, which, as you see, requires quite a level of expertise to operate. So the objectives with this workbench were twofold. First of all, to provide a fairly easy to use CFD add-on for FreeCAD, and secondly, to make OpenFOAM more accessible by providing a fairly simple GUI for it. And the advantage of using FreeCAD for this is that one ends up with an integrated CAE solution with the CAD and the CFD analysis in one place, which is very powerful. So a bit of history on this. Most of the development was done about 5 years ago when I was working at the Council for Scientific and Industrial Research in South Africa with some colleagues of mine. And the idea was to provide easy access to cold flow modeling capability to engineers at Eskom, the state electricity company. The idea being to put basic CFD analysis tools in the hands of a much larger proportion of the workforce than those that had access to the commercial modeling tools. And this followed the successful adoption of the FEM workbench at Eskom, and that was estimated to have generated about an 8-fold return on investment if one looks at the cost of performing the equivalent simulations in commercial tools. These projects were championed by Michael Hindley, who some of you may know as the user Makamal on the FreeCAD forum, a really wonderful man and sadly no longer with us. And he had a great enthusiasm for open source software. So CFD-OF was initially created as a fork of the CFD workbench by Xingfeng Xia. One doesn't like to see lots of forks being created. Unfortunately, our hand was a bit forced by the fact that we had very tight deadlines on this project and needed to be able to make decisions very quickly. Originally, our hope was to eventually merge it back into the CFD workbench, but in the event, it turned out that our philosophies had somewhat diverged and it just made more sense to keep CFD-OF as a separate project. So since that original project, I have been largely maintaining the workbench in my spare time, trying to smooth off some of the rough corners and increasingly getting some contributions from the broader community. So it's perhaps appropriate here just to say a little about the motivation for looking at open source solutions for projects like this. An obvious reason is to have a customized solution for a client. One other major motivator is to not be limited by licensing costs in terms of the number of runs and the number of parallel processes one can use. And this in turn allows many more engineers to be part of the design loop and avoid the situation where you tend to have CFD done as an afterthought after the design has been made. One is in funding a development project like this, investing in local skills and people often rather than sending license fees out of the country. And a company maintains control over their full engineering pipeline. The CFD is not a black box, which you don't know what's happening in. And that occurs over the full lifetime of the product, which in the case of something like a nuclear power plant, of course, could be decades and decades. And over that time, one has security on the end user license that can't shift under one's feet. So as I said, the CFD-OF workbench is a simple front end for OpenFOAM. It must be said that it only scratches the surface of all the features that are available in OpenFOAM. But the idea is hopefully that one will be able to tweak the case setup that's written by CFD-OF for the more advanced cases that you might want to apply it to. And one can also ship these cases off for offsite computing on a cluster, for example. And we've tried to keep the installation nice and simple through the FreeCAD add-on manager and with the dependency installation all centralized in place in the preferences page. In terms of meshing, 3 meshes are supported: the OpenFoam native Snappy Hex mesh, CF mesh, which is a third-party OpenFoam based mesher, and G mesh. CF mesh we've found tends to be a good choice for external aerodynamics applications with lots of boundary layers. The good thing about both CF mesh and Snappy Hex mesh is that as cut cell Cartesian volume meshes, they tend to be quite robust to dirty geometries. One doesn't need to have a fully watertight geometry as long as the gaps are smaller than the cell size. It copes quite robustly with these dirty geometries. In terms of solvers, at this point we support single-phase incompressible simple foam solver in OpenFoam and the buoyant compressible solver. Then the free surface solvers, interfoam and multiphase interfoam, and a solver that was also developed at the CSIR called HISA, which is a high-speed coupled solver intended for transonic and supersonic external aerodynamics applications. In terms of visualization, we've handed this all off to an external program called ParaView, and the reason for doing this is that CFD meshes typically tend to be between tens and thousands of millions of cells in size, and ParaView is already very well optimized for handling these sort of enormous data sets. So here we just have a short example of a typical analysis one might want to do using the CFD-OF workbench. Here we're just importing a CAD geometry, and this is an example of a somewhat dirty geometry that's not a watertight solid. Here we're just choosing to remove the propeller from the back of this geometry because obviously simulating a propeller that's stationary is worse than just simulating the propeller at all. And what we're doing now is to cut this geometry in two. It's something that's often done in CFD just to halve the computing time if you do have a symmetrical situation. And now we are going to add an external flow domain to this. And that will allow us to simulate the flow around the outside of the body, and just creating a compound of the two will effectively subtract the body from the outer flow. So we create a CFD analysis here, and the first task is to generate a mesh. So we start with a very simple case without any mesh refinements. And you can see here that on the file system, a OpenFoam case directory has been created with a run script for the mesher. And we run the mesher just to see what this initial mesh looks like. So we have built in a check mesh functionality that one can use just to make sure there are not any major errors in the mesh. And everything is okay on that here. Then we also have just a very quick way of visualizing the mesh, just to load the outer surface of the mesh in freecad. If one wants a proper visualization, one does need to load the full mesh in ParaView. So as you saw from that mesh, it was horrendously too coarse. So what we're going to do is create a mesh refinement on the body. So we create this mesh refinement zone, choose a relative element size of 0.02, create some boundary layers to better capture the viscous layer of flow around the body, and we add the body to that. Then we're also going to create a volume refinement, which extends further around the body. One can create any shape for this, in this case, a sphere. And then we create a volume refinement zone where we refine the cells to 1/4 of the edge length in the outer mesh. And having done this, we are then just going to rerun the mesher and see how the mesh looks now. Fair disclosure, this is sped up quite considerably in the video. And you see the CF mesh output running there in the report view at the bottom of the screen. So we open this in ParaView now. I wasn't entirely central with my volume refinement zone, but that's not a problem. And as you see, if we zoom in on this, you can see the boundary layers that are around the wing. And then switching to looking at the surface mesh on the body, you can see that the undercarriage is not captured brilliantly. There's a bit of jaggedness there. So what we're going to do is just show an example of creating another surface refinement zone on just the undercarriage itself. And this is the sort of thing that freecad really makes so much easier than manually generating an open foam case yourself on the text interface. So we run the mesher again. And having a look at it once again in ParaView, you can see that that undercarriage is now much better captured. Okay, so that's the mesh. The next step then is to create boundary conditions for this analysis. So here we specify a slip wall on the body itself, and then we're going to specify the internal plane about which we wanted to have symmetry as a symmetry plane. And the external plane we just set to be a slip wall. Now we would like to simulate this aircraft at an angle of attack to the incoming flow. And the way this is usually done is to vary the angle of the incoming flow rather than the geometry itself to avoid needing to remesh it. So we're setting both the front and bottom planes as inlets and setting fixed velocity there. And then having done this, we're going to set the top and rearmost planes to a pressure outlet, which is the standard outlet that's used in incompressible flow. Okay, then there are various other parameters that can be changed. We're just renaming some of the boundary conditions. So in the physics model, one can change the type of analysis. And here we're doing a steady state analysis, single phase flow, incompressible with turbulence. And we are using air as our material. This allows us to choose an initialization for the fields. For a steady state analysis, that's not usually too important. We just set the velocity to potential flow, which gives an initial estimate to speed up the convergence of the simulation. And now what we're going to do is add a reporting function. This allows us, in this case, to view the forces on the body in real time as the simulation progresses. And there are other reporting functions for force coefficients and probes at certain points in the domain. So having created that, we now start running the solver. And you'll see as we run it, both first of all, the case directory that's been created here. You can have a look at the input file for the velocity and how the boundary conditions have been written here. And the FE schemes file, which gives the numerical discretization schemes that are used by OpenFOAM. When we run the solver, we have this prompt. It's automatically detected that some changes have been made that affect the mesh, and so we're prompted to remesh. And as we run the solver, we can see the convergence of the forces on the body and the convergence of the residuals, which is basically a measure of how well solved the steady state problem is. So opening this in ParaView, one can interrogate the results. In this case, we're just going to have a look at the pressure plotted on the surface of the body. So a very useful feature of freecad is this ability to record macros. So as you can see here, as I tweak certain parameters, I get a live output of the equivalent Python code that would have that effect in the bottom right-hand corner in the Python console. So having made these tweaks, I've recorded a macro. And if I open that macro, I'm just going to make some changes to that to automatically do a sweep through these parameters, a sweep of this aircraft through different angles of attack. And what that's going to allow me to do is to generate a variety of different cases that I can then ship off for offsite computing if I wish to generate the data for this sweep. So I've run the macro and those cases have already been generated, and you can see them here, these 4 OpenFOAM case directories. And here you see the modified velocity in one of these examples as the inlet velocity. So that was just a whistle-stop tour of a typical type of analysis that one might want to create with CFD-OF. Some of the other features, one that was often requested is the ability to import multi-region STL files directly. So instead of necessarily creating the CAD in freecad, if one has a pre-faceted file like the one sees at the right here for this rocket, to be able to cope with the large number of facets that are present was a bit of a challenge, but something we've improved considerably. And you see the example of the simulation in the bottom right corner. We've also added mesh adaptation, an example of which you see here for shockwaves. It's also available for multi-phase interface. We've made various updates to CFmesh to make it more suitable for use with CFD-OF. We have a suite of regression tests which allows one to conveniently see if one has broken anything when developing the code. And we have a templated case builder, which basically is a set of template files which define the OpenFOAM case files, and this makes it very convenient to be able to expand the code to other solvers, for example. These files take the input quite directly from the Python code and prevent having to write too much boilerplate text file output code. Then various other features that have been added, support for LES analysis for these reporting functions, scalar transport functions. Thank you very much to Jonathan Berg for his input in those. And then we have a bundled Docker installation that allows one to basically install all of the dependencies as a single Docker file and speed up that process quite considerably. Just a quick overview of the uptake around the world. At the moment, we appear to be running at around 200 installations of the workbench per week, and that's remained roughly constant between 2020 and now, with a roughly equal Windows and Linux split. So there are many applications of this that people have shared on the forum. We don't have time for all of them, unfortunately, but this is just one example, which is perhaps notable in that it has an experiment associated with it, and good agreement was reached between the experiment and the simulation of this vortex generator device. Thank you to Michael Slee for sharing this. So we welcome many and all contributions. Probably, I think the most urgent thing for now is some written documentation. There isn't anything at the moment, and it would be great to have something official on the FreeCAD wiki. But the list goes on almost indefinitely. And I'd just like to say some thank yous to Johan Haynes and Alfred Bogars, with whom I originally developed the workbench, the original creator of the CFD workbench, of course, as I mentioned, Michael Hindley for being the driving force behind this. And then I think the companies ESCOM and CSIR do deserve credit for agreeing to release these packages as open source. Thank you to all the contributors listed here and those that have created training material on YouTube. Particularly, I must say thank you to Thomas Schrader, who's been ever present on the forum since 2017. And I'm not sure if we would have any users of the workbench if it wasn't for the help he'd given to all of them. Finally, I'd just like to thank my employer, Engis, for tolerating my hobby of tinkering around with CFD-OF. So that is a very quick intro to the workbench. I hope you'll go and try it out for yourself. Thank you for your attention.
When I'm done with my studies, I will definitely feel like I'm ready for work, mainly because I had enough time to prepare to be a vet. So we do have like a skills lab where we have models, so we get to practice on models before working with the real animals. Apart from that, our final 2 years, we will be doing clinical work, so we get enough time to consolidate everything which we were taught and to practice every skill up until we perfect it in the hospital prior going to the real world. The veterinary profession itself is so vast, they have a lot of opportunities. So I know some might be thinking like, okay, veterinary science is all about dogs and cats, but there's more to it. You can do anything, ranging from parting meat inspection, game, like working with wildlife. So the list is endless. So definitely I would recommend someone to study veterinary science.
Good afternoon. I'm Cecil Cherms, and thank you for the opportunity of bringing to you an introduction to the NICREDAP freecad workbench. This workbench will operate on any assembly which has been put together with the freecad assembly 4 workbench. Given that assembly, it can then model from it a full mechanical assembly or mechanism with joints and forces and such like. On this system, it can then perform planar dynamics analysis, hence the acronym DAP. And once that dynamic analysis has been performed, it will output both kinematic and kinetic data for all the objects in the subsystem. It will also, on request, display a full visual animation of the analyzed system. Hence, with freecad's ability to design and build 3D objects of arbitrary shape, and Assembly 4's ability to put those objects together, so the NICREDAP workbench can take that system or assembly and analyze it, give you all the velocities, accelerations, Lagrange multipliers, the works for every single object, every single subbody, every single point that you have defined specifically for that subsystem. And then also display a full visual animation of that system so one can see exactly what is going on. Now, when I mentioned a full planar dynamic analysis, I'm sure that many of you, similar to this gentleman in the picture, were dreaming of a highly complex system. And NICRADAP can handle such a system, but the 20 minutes of my talk cannot. And so this type of a complex system will have to wait until next year's conference, when you are more well aware and au fait with how freecad NICRADAP works. But I'm going to show you just a very basic, simple assembly so that you could get an idea of how NICRADAP is run. To illustrate how NICRADAP works, I'm going to take a very simple example, the example of a pendulum, a simple pendulum. Now, I assume that you've already made some shapes, some solids, and that you have, using assembly 4, assembled these into some or other assembly. And so in this case, we have a ground box at the top, a lug attached to the ground, another lug attached to the pendulum, the rod of the pendulum, and the bob of the pendulum. Now we are ready to use NICRADAP. So we call it in the workbench list. Now, all of the assembly 4 parts are assembled under the heading parts. The links to the parts are assembled here under model. So for our DAP work, we need another container here into which we can put all of our DAP parts, and that we refer to as a DAP container. So there's our DAP icon, and I create a new DAP container. Right, so now that contains all of my DAP bits and pieces. I want to define a body, so I click that, and the first body is this one up here. So it consists of ground, so I add that, and then in the list I add the lug and ground. Then it's not going to be a moving body, so we switch that off, and that's okay. Now we define another body. This is going to be the pendulum. So it's going to consist of the pendulum lug, the pendulum rod, and the bob. And if we say OK, and we now hover over the first one, there's our ground body, and there's our pendulum body. So I can rename them just so that we know what we're talking about. So I'm going to call this DAP ground and call that DAP pendulum. Right, now between the two there's a joint, and we have to define this joint. We have to tell the system about it. So we go to joints, and the joint is in this body and in that body. So I can now select the one body, it's the DAP ground body. Which LCS, which local coordinate system, are we actually going to, are we referring to when we refer to that point? Are we refer to the lug hole? So that's what we select there. Then the other body is the pendulum body, and which LCS here are we referring to? That's all that are available, and that's the one that I want, the lug hole. So if I say OK, I then have a decoration up here which tells me that is the point that I have to find to be a rotation point. Now I could have chosen lots of other types of joints. If I just go back to here, and those are all the types of joints that we can define, but I've just defined that one for simplicity's sake. Right, now we've defined our bodies and our joint, so we now need to define the mass or the density of each of these bits and pieces. So I go to my define materials, and there are the list of the bits and pieces that make up my system. Doesn't matter what the density I give to the ground because it's not moving. So the pendulum, I can give it a density, or I can say just ignore it. Ignore its density. Make it very small. And let's make the bob out of steel. Okay, so there are densities, either in kilograms per cubic meter or in grams per cubic centimeter, whichever way you want to input them. Right, now that we've done that, we can define a force, more than one force, but in this case we're just going to find one. There are lots of forces to choose from, springs and rotational springs and dampers and all that type of thing, but we're just going to take the simple force, gravity, in the minus y direction, minus y. And now we've defined everything, we can now simulate the motion. So I go to run the analysis for 10 seconds, 100th of a second at a time. Accuracy, less accuracy is faster calculations, but less accurate values, etc. So we ask to solve this, which it now has done. And so now I can go back and say, animate, please. Play. And I can push up the play speed. And there's our animated pendulum. Right, so now what I can do as well is revert to my analysis. I could have done this first time around, but we're going to do it now. I'm going to select that I want to output the full data. I can now give it a name, simple. And now, not only will it calculate this for the pendulum, but it will output data to a space-separated spreadsheet file for your Excel or your LibreCalc or any other spreadsheet of your choice. And using that, you can analyze, further plot, and see what's go into more depth in the actual analysis of the system. So I request solve, and because I've asked for a little bit more accuracy and we're doing the full data, it takes slightly longer, but that's now done. So I'd like to okay, I have now loaded up a much more complex pendulum system, and we're going to analyze this with Microdap and also animate it, and also see in the results what this one's parameters look like. On purpose, I've made a simplification, and I've made all of these connecting rods to have almost no mass. You know, a typical simplification to help you to do this by hand. And we will see how horribly wrong you can go by making simplifications and not using a program like Microdap to actually do the calculations correctly. So we're now going to go to the solution part, and we're going to have 1 in 100th of a second time steps. We're only going to do it for maybe 3 seconds and see what it looks like. Now, this is a rather old, slow laptop, so it will take a little bit longer than on a nice, fast new one. But the times are not unreasonably long. Okay, our calculation is done. So we can close this and go to the animation. Speed up the animation a bit for the sake of time. And play. And that gives you an idea of the complexity of a pendulum system that DAP, for instance, can handle. Okay, let's look at a small subset of the parameters that Microdap generates in its analysis and which it outputs to the spreadsheet file. Here's something relatively trivial. A simple pendulum, a sine wave, what looks like a sine wave for total kinetic energy, total potential energy, sum of the two is constant. However, when we go to a more complex pendulum, the possibility of calculating this from scratch is relatively remote. Even though we're just looking at total kinetic energy, total potential energy. However, what we do have as a check, their sum is still constant. If we now go back to the simple pendulum, just look at its motion, the x motion of the center of gravity of that bob there. We get that. Plotting x as a function of time, plotting y as a function of time. And that looks like a sine wave. However, when we look at the velocity, in other words, the slope of that position time graph, we see that by no means is that a sine wave, because its velocity is almost a triangular wave. And look at the kink over here in the x velocity around the 0 point. Somewhat unexpected, especially to people that think that pendulums are an example of simple harmonic motion. They aren't. Only in the limit very close to their equilibrium point do they follow a sine wave. So we also look at the acceleration, and that is even more complex, just for a simple harmonic, a simple pendulum. If we now go and plot it in a different way, we just plot x versus y position of the center of mass of that bob. We get something simple like that for a simple pendulum. Velocity and acceleration. And the reason why I'm showing you it in this form is that it's easy to look at the more complex pendulum in the same type of form. That's the X and Y motion of the center of mass of that bulb over there. And you'll notice that these points are the motion is very pointy there, because on purpose I've approximated this pendulum to have close to zero mass in all of the connecting rods, the connecting links. And I did that for a specific reason, to show how one can analyze such simplifications. Right, so there's our position, there's our velocity, and there's our acceleration. Massive accelerations wherever the bob needs to change direction. 9,000 meters per second squared. And that is because we have now approximated these to be relatively massless. So what happens if we now, in NICRADAP, go back and we add density to all of the connecting rods, whatever density we wish? When we do that and redo the analysis, we get a different path, but you can clearly see that as it changes direction, there is a lot more finite acceleration taking place. And that's a plot of its velocity only in the first 3 seconds of its motion. And that is a plot of its acceleration in the same scale as the previous one. So if we compare the two, we see that the same system with the simplification gives a rather different result to one which is more correctly set up according to the actual system that we are studying. It is my privilege to announce that as of today, 1st of March 2023, the NICRADAP freecad workbench version 2.0 alpha has been released. It is now available for download from the GitHub repository. The address is given on the screen. If you are not used to installing freecad workbenches, then probably this short list of instructions should help you along the way. It isn't really difficult to install it. Remember that this is an alpha release. There are going to be changes, there are going to be bugs, there are going to be new additions, but we felt that it would be good if everybody, as from this conference, could have a look, try it out, and see if you like it. Sure you will. In conclusion, I'd like to acknowledge the contributions made by others towards the success of this workbench. Professor Parviz Nikrabesh of the University of Arizona in Tucson was the developer of the algorithm on which this work is based. I would also like to acknowledge the foundation that was built by the authors of the Revision 1, because on this foundation I was then able to build Revision 2. We would also like to thank our sponsors who have made the development of this workbench
Engineering 4.0 is a response to the opportunities enabled by the fourth industrial revolution to create smart cities, smart mobility, transport networks, and intelligent systems. It further demonstrates that partnerships and collaborations with the public and private sector, in this case, SANRAL, the CSIR, and York Timbers, can help solve some of South Africa and Africa's pressing challenges. Engineering 4.0 will share its vast resources in technology and data with all faculties via the University of Pretoria's Future Africa Institute, a platform for developing inter- and transdisciplinary research networks within the university and the global research community. This research facility is a first for Africa and focuses on sustainable transformations of society.
Hi there. This is a video on the Beltrami workbench in FreeCAD. I am Michel Sabourin, and you are on the SimTube channel dedicated to hydraulic turbines. This video is part of a series on the Beltrami workbench in FreeCAD. Beltrami is a tool to design any type of turbo machine blade. It can be turbine, pump, fan, propellers, etc. All of them have the same topology and the same mathematical representation. Here we have a Francis turbine blade for the runner. We have also here the blade for the distributor. It's a wicket gate. And we can see the assembly of both here. Another type of geometry that is quite frequent, it's the Kaplan blade. Here we have the complete runner assembly. And here we have a blade for a pump and the complete assembly of the pump. So Beltrami can do any type of geometry for turbo machine. It works on the principle of modifying an existing profile. We can start from an existing geometry, or we can use the original profile that is embedded in Beltrami software. Let's start from scratch. I activate Beltrami, and Beltrami has two buttons. The first one is to start a profile from scratch, a cold start. And the second one is to modify the profile. Let's start. And this is the profile that is embedded in Beltrami. The information is classified in various groups. The first one is the user interface. And the last one is the 3D result. All the other are a kind of virtual plane that are used for mathematical calculations. Let's take a look to the user interface. There is three entities there. The first one, parameter, is a feature Python that is used to structure the data. The parameter here is cascade rotation, so it indicates if the blade is rotating or not. The second one is the number of blade in the runner. It's only for documentation. And fillet is the number of curves. If I reduce to 3, immediately that there is one there, one in the middle, and one at the end. If we go to 9, it increases the definition of the blade in the transverse direction. Here is the number of points defining each curve. Presently, there is 9 points. If we increase to 19, to 129, it influences mostly the leading edge shape. And in fact, it should be increased for fabrication, for calculation for finite element or CFD. But during the work on the geometry definition, it's not necessary to have it so high. So we keep it at 9 to maintain the reactivity of the software. And here we have the sense of rotation. So this is the positive, which is counterclockwise. If we put it negative, we have the clockwise rotation of the blade. The other interesting entity here is the sketch meridian. If we go in the sketch, there is 12 points defining the contour of the blade, and these points can be modified to suit your requirement for your design. So in that plane, here we have the leading edge, and there is the trailing edge, and the flow go from the leading to the trailing edge. If we do a modification, so we can move it, we can pull down a single point, we can displace any of the point here. Before closing, I will switch to constraint to lock all the position. And when I close the sketch, automatically the contour of the blade in the meridian plane is corrected and the 3D geometry is obtained accordingly. The spreadsheet Tableau Pilote is used to define the shape of the blade in 3D. In green, it's for the shape of the web, and in blue, it's for the thickness law that is built over the web to obtain the pressure and suction side of the blade. Let's display only the web. The first data, theta, define position of the leading edge and of the trailing edge. So for the leading edge, the position in degree is from 0 to -4. From 0 degree, you see, to -4 here on the top. And there is 4 poles that model mathematically the value. If, for example, we wish to lean the blade on the other side, we can just change the sign here of the variable. We can see the effect by using the update button here. And we obtain the result immediately. If, for example, we wish to have the trailing edge on meridian plane, let's see, presently it's from 30 degree to 60 degree here, from 30 to 60. Wish to put at 40. And again, I update the profile, and we have now the trailing edge on the meridian plane. Alpha are the angle at inlet and at outlet angle of the blade. So presently, the angle is -50 degrees around for the inlet. So it goes in that direction there. If we wish, for example, to have a 0-degree inlet angle, we can put 0 there. And we have a 0-degree inlet angle for the web. Of course, all the other surfaces follow automatically. As the alpha angle influences the energy transfer between the fluid and the blade, it is interesting to take a look how this angle evolved from inlet to outlet. And this is found in the virtual plane plan cascade. Here we have, for each fillet from 1 to 6, the evolution of the angle. Let's look at the first one. So we see the angle is 56 degree at outlet and 0 degree at inlet. We see also that there is a little inflection here in evolution of angle. It could be desirable to remove this inflection or to correct it slightly by decreasing the length of the blade. This can be performed by reducing at the bend your angular position. If we put -30, we see the effect here. We shorten the blade at the bend. And if we come back to the cascade, so the cascade is more regular and more interesting from a fluid analysis point of view. Now let's take a look how these pressure and suction side are built. There is 5 points defining the thickness law that is used. The variation of thickness are defined in the group plan épaisseur. There we can find 6 sketches corresponding to the 6 fillets. For this Francis profile, all the 6 fillets have the same thickness law. Let's take a look to the sketch for suction side at the bend. The leading edge is at the left and the trailing edge is on the right side. On top we have the suction side. It's not in the sketch, but we see the pressure side of the other fillet. The virtual length of the profile there is 1000. There is 5 poles that control the curve. The first one here, the second, the third, and the fourth and the fifth are at trailing edge for this type of profile. The position of these 5 poles are defined here in the spreadsheet. So there is the 5 poles, EX for the suction side, and IN is for pressure side. The 5 points and the X coordinate and the Y coordinate of these poles. All these values are scaled to fit the 3D length of fillets. Pole 1 is on vertical axis here. That way it ensures the continuity of tangency between the suction side and the pressure side. Pole 2 influences the thickness as well as pole 1. Pole 3 is on the x-axis to make sure to have an horizontal tangency at trailing edge. Pole 4 and 5 are at trailing edge. If we keep the full length of the virtual profile here, we will have a zero thickness at trailing edge. This is why we have another variable, a pilast for suction and pressure side, that is used to truncate the profile during the discretization process. We can observe that here. These are the points that are retained to define the thickness law, and these points define the length. So this is the last point and the true trailing edge here. So this trailing edge will have a non-zero thickness. If we display the 3D result with the web, if we want to increase the thickness at the crown, so the thickness at the crown, the maximum, will be defined at the pole 2 on Y definition, and presently it's 50. If I put 100 and launch the calculation, we see that everything on pressure side remain constant, but we see that the profile has been modified on the suction side at crown, but not at bend. This kind of evolution from the bend to the crown is calculated in the pilot group, where we can find the variable we have modified, which is APAX2Y. APAX2Y, it's here. And if we look at the sketch there, we see that we have 100 millimeter for the point at crown, and 50, and in between, the curve that is used to define the thickness for each of the fillet from the bend to the crown is there. You have to realize that all these virtual planes give a good documentation of what is happening in the profile, but they must not be used to modify the profile. The modification of the profile must be done always from the spreadsheet. Before to end on this profile, just a few words on the results in group Domain 3D. The raw result of Beltrami method is contained in group points. Here we have the points for the web, here is for the suction side, and the point for the pressure side. Also we have here pressure and suction side assembly. So these points are exactly the same than the other, but they are in a single series. Following this series of points, we have curves for the web, for the suction side, for the pressure side, and also here we have the assembly of suction and pressure side. Then from these curves, we make some interpolation to create the surface. So we have the web, the suction side, the pressure side, and the complete surface of the blade. In the process, the tangency conditions of the complete blade surface is transferred to the pressure and the suction side. Just to complete the demonstration, I will increase the number of points, and we will see that the discrepancy here will decrease. So 19 points, 120 points. At 121 points, there is a perfect fit of all the surfaces. Now, let's go to the final example, the radial cascade that demonstrates the powerful capabilities of freecad in parameterization. Here we have a Gadvain profile. This profile presents a simple contour in the meridian plane. It's a rectangle. Here in the spreadsheet, the rectangle position and size can be controlled, adding some simple instructions. The yellow background indicates the variables that can be modified. Here is the radial length of the profile. Here it's the distributor height. And finally, we have the outlet radius. This is the radius there. If we increase the radial length to 200, immediately the profile is modified, but the rest of the spreadsheet is not updated. We need to do the profile update here to obtain the value updated for the rest of the spreadsheet. If we look at the alpha variables, we see that we wish to have the same angle at inlet and at outlet. Moreover, it will be desirable to have a constant angle value between inlet and outlet. Let's see what we have presently. So we go in virtual plane plan cascade and we open the sketch. We have the two angles at inlet and outlet, but in between it's a curve. It's not a perfect line. It will be desirable to correct that. We have to modify the length of the profile. So we have to increase this value here. Moving this point up, we will have a straight line at some point. The spreadsheet suggests a value to adjust the theta outlet to obtain a straight line. I use this value and launch calculation. So it moves slightly a bit the outlet. It suggests to increase the value to 1282. You understand that we are in an iterative process and we have to iterate until we are satisfied with precision. So finally, we converge to this value. So both values here are the same. Let's see now at the sketch, and you see that there is no variation in the angle from inlet to outlet. We can observe that the shape of the web is not a straight line. This demonstrates that the spreadsheet expands significantly the parameterization possibilities in freecad. On the website simtube.com, you will find a lot of information on this method. All the references that I will give are included below in the description. First, there is the SimTube YouTube channel in which you will find a playlist on Beltrami. Then there is theoretical information on hydraulic turbine there. But for methods and tools, it's here. And you will find realization of the hydraulic profile of 3D turbomachinery blades. There is some theoretical aspect. So it's the analytic formulation of the method. There is also the numerical formulation of the method. And finally, you will have the user manual that you can access here. And in the user manual, you will find that modification of the hydraulic profile. You will find all the information on the way to modify the blade here through the user interface. So there is the three entities that can be modified: paramètre, tableau pilote, and the sketch meridian. Inside paramètre, you click on it, you have the picture of the screen, and you can access each of the point here identified. So that way you have a good description of all the variables. For tableau pilote, it is the same. And the complete description is given here, and it is fairly complete. So this is the end of my presentation. Do not hesitate to contact me if you have any questions or comment. Thank you very much.
If you look at our world today, the challenges are just so clear for us all to see.
Climate change, it's an existential issue and it's going to need engineers to come up with solutions.
Engineering has a really crucial role to play in helping us to deliver jobs and opportunities.
In collaboration with our fellows and partners, the Royal Academy of Engineering harnesses the power of engineering to help build a sustainable global society and create an inclusive economy that works for everyone.
My research is in the development of batteries, finding ways of storing energy that is intrinsically low carbon is really important. The research that I'm doing is completely underpinned by the support of the Academy.
We support talented engineers like Paul at every career stage and work with teachers, researchers and employers to make the profession more resilient, diverse and prepared for the future.
Engineering in the UK really still has a serious diversity deficit.
Better engineering solutions will come from having a diverse group of people working together.
The Graduate Engineering Engagement Programme helps graduates from underrepresented backgrounds into the engineering industry. It was incredibly beneficial to my career.
The Academy backs the people behind innovative businesses through our Enterprise Hub.
NitroPep creates surfaces which self-clean. So they kill bacteria, they kill viruses, they kill fungi, and it protects people from surface contamination. Having a mentor who's a really experienced business person was absolutely valuable.
It's a great privilege being a mentor, and it's a responsibility. And becoming a fellow, this is made very clear.
Our global entrepreneurship programs train innovators worldwide to commercialise their work, and we bring together the world's best engineers in collaboration with other professions to form international partnerships addressing some of the planet's biggest challenges. We engage policymakers to ensure government has the best engineering advice. Our National Engineering Policy Centre provides independent guidance, drawing on the expertise of more than 450,000 engineers.
The Academy's been extremely helpful in areas of energy, in particular looking at hydrogen. The Academy has a wide systems view of the whole of hydrogen, from its generation, production, distribution and the like. And by providing us with that understanding, we can see the bigger picture.
We also engage the public. Our This is Engineering campaign opens the eyes of millions to the wonders of engineering, challenging preconceptions and showing how engineers make a difference.
I see extraordinary talent and passion in the engineering community.
I'm enormously optimistic about the future.
Everything that wasn't invented by God was invented by an engineer.
The Academy started life in 1976 with the support of His Royal Highness the Duke of Edinburgh. 130 of the UK's finest engineers were enrolled. People who over the course of their careers had literally changed the world. Engineers like the jet engine visionary Frank Whittle, bouncing bomb inventor Barnes Wallis, and Lord Hinton, who'd driven the UK's supremacy in nuclear power. 1976 saw some notable engineering milestones. Concorde made its first commercial flight, Apple launched the Apple I computer, and the Viking 1 and 2 probes landed on Mars. The Academy brings together the most distinguished engineers in the UK.
It means you're recognised as somebody who's made a very big impact in engineering and as a senior voice in engineering, and also as a role model that can help set the agenda and the tone for others to follow.
I was always fascinated by things that moved, by prime movers, by engines. I just became interested in what made it all tick.
Before I was elected as a fellow of the Academy, I thought of the Academy like the leading body for the engineering profession, speaking with one voice for the engineering profession.
Within the Academy's fellowship, people who really know how to turn ideas into reality, and that reality into jobs, into economic growth.
The Academy has grown steadily to undertake a key role in policy advice, whether it's sustainable energy policy, water resources, infrastructure, and secure communications. We are a national academy, but we have a global outlook. In our international activities, we have many research and innovation programs which are aimed at growing emerging economies. In sub-Saharan Africa, we're working with universities and businesses, growing capability in teaching, research and innovation.
If we look at what has been achieved through phenomenal engineering innovations, like for example the internet, it's an engineering innovation at heart, delivered by engineers, and it's transformed society. Our lives are completely different now to the way they used to be. That's what engineers need to be proud of.
Through the establishment of our Enterprise Hub, we bring together young entrepreneurs and provide mentoring from within our fellowship.
And at the Enterprise Hub, what we do is we work with aspiring entrepreneur engineers, people who want to take what they've built, take what they've invented, and really go out there and sell it.
Being part of the Hub has been incredible. The mentorship, the access to all the experienced entrepreneurs has given me the freedom to come out of the academic environment and start my business.
The Academy hosts the Queen Elizabeth Prize Foundation, an international £1 million prize awarded every 2 years for groundbreaking innovation of benefit to humanity. It recognises engineering excellence and is designed to inspire the next generation of engineers. In 2015, the prize reached a worldwide audience of 1.25 billion people.
We're trying to get people away from the boots and hard hat image of engineering and see it for what it is, which is providing solutions to all of society's problems.
Engineering's ongoing role in shaping the future and making the world a better place relies on encouraging talented young people to take up engineering careers. We put a lot of effort into promoting engineering to youngsters, showing them what engineering is all about so that there will be a ready flow of young people thinking of engineering careers. It's those young people that are our future.
The Royal Academy of Engineering came in to help us make propellers. We tested them to see how high they could go, but mine didn't go very well.
In 40 years' time, I would see an academy that has much more influence. I'll see an academy that's doing many more things with more resource and that's making a bigger difference. And I will see a society that has engineering at its heart and recognises it.
If I was an engineer, I'd do a lot of different things and create the rocket shoe, robot fairies, rainbow iPads.
I would like to see engineering helping in finding the solution to big problems such as energy and the environment.
We're going to see a lot around space travel and space exploration.
In the future, I would like to see the Academy become the go-to place at the heart of the UK for engineering.
I think the role of the Academy is to inspire young people.
Particularly attracting more girls to engineering. It isn't a male subject, it is a people subject.
I'm incredibly proud of everything the Academy has achieved in its first 40 years. And I'm grateful to our fellows, staff and partners and supporters across academia, business and government who've worked with us to make this happen. And I look forward to the next 40 years working together.
Good morning, good afternoon, and good evening to everyone across the globe. For the first time, I am showing my face. My name is Vanu Govender. I am one of the organizers of the FreeCAD and Free CAE Users Conference for 2023, hosted by the University of Pretoria. And as you watched, proudly sponsored by the Royal Academy of Engineering, Engineering X, as well as the Engineering X mission, skills where they are most needed. Due to some technical difficulties as well as some miscommunication over the months, the last presentation will be presented live by Hiroshi Okuda. He will be presenting frontal STR, or a spin-off of the FEM module. I hope you guys had an absolutely fantastic experience wherever you are in the world. After this, we'll be concluding today's version of the conference and starting again tomorrow at 12 o'clock GMT 02 South African time. I really hope you guys enjoyed today's version of the conference. If you have any questions, anything that's unclear, you are welcome to drop me an email or just drop me a message on the FreeCAD forum. I am Vanu01. That is my username on the FreeCAD forum. So on behalf of myself and the University of Pretoria, I'm now going to hand over to Hiroshi Okuda from the University of Tokyo, all the way on the other side of the world, where he will then present the final segment of the conference. I'm now going to hand over to him. You're welcome to share your mic, share your screen, as well as your slides, and let's wrap this thing up.
Varnu, do you hear me? So now I'm trying to share my screen. Just a moment, please. Okay. So now, do you see my screen? Okay. Wow. Now, okay. First of all, I apologize for my making you trouble. Now I hope my screen is now shown. Can I continue my talk? Okay. First of all, I apologize for my trouble. I was late sending my video, and I tried to keep my presentation using just my slide, but Varun had helped me to do my presentation alive. So my name is Okuda, and the title of my talk is Add-on of Frontier Start to FreeCAD. And so I try to keep my time, and but this slide is showing the contents of my talk, starting from introduction. I will show our recent activity to develop the workbench named Front ISTA workbench, which is a nonlinear finite element analysis program. And actually, we are rather new guys in the community of freecad, so I'm a little bit nervous how our talk is matching your interest, but I try to present something. Okay. So first of all, just I'd like to introduce what the Frontista is. It is actually the nonlinear finite element analysis program. This slide shows a brief history of Frontista. Perhaps we have started developing this program from maybe 25 years ago. At the time, Japanese government had started to develop the very large-scale parallel computers called the Earth Simulator, and we joined that kind of that project, and we redesigned the finite element analysis program, which can utilize the data structure which match the vector machines, and continuous short-term project. We have continued developing this program. Sometimes it was ported to the K supercomputer, and right now is a Fugaku supercomputer. But at the same time, we are trying to distribute the outcome of a finite element program to the industrial side, and we have established an non-profit society called Frontista Commons. And as a part of the activity of Frontista Commons, we have recently added the Frontista workbench onto the freecad. And so today I just introduce our recent activity. So, and this slide shows some comment about the importance of openness. And perhaps you may have already mentioned about these. So I'd like to skip to explain this slide, but just I'd like to focus on one point, which is that to share the finite element program is a very efficient and important way to keep the transparency. And but as for the input data like mesh physical properties or other database about the materials that can be kept among inside the companies or industries. So that is one important point of the openness or open source code programs. Okay, and this slide shows the very general expression about the CAE procedure here. Not only in the structure analysis, but also in the CFD area. We may start from the modeling and the pre-processing. Pre-processing includes mesh generation and the setting boundary conditions or setting the material parameters. And perhaps afterwards, various kind of finite element programs can be applied. Then afterwards, we visualize the result and evaluate the results. But since the finite element solvers are so fast or developed, which are very suitable for the parallel machines, but perhaps over 90 or 95% of the total time may be used in the pre-processing, including the CAD modelings, consumed throughout the CA procedures. And always the pre-post processing is the importance of pre-processing or post-processing is an old and new issues. And we have been looking at various strategies for building all-in-one environment. We may have taken various ways, but today, as we've spoken today, we have recently focusing on the freecad capabilities, CAD modeling or its function to extend or to incorporate the workbench from outside. Okay. And also, we are considering these two computational environments. The one is the local use personal computer only, just your local environment. You will do all the CA process. But at the same time, we encounter such environments that when you develop your models, you may use your local machines, and finite element large-scale computations are done in our local PC clusters, remote PC clusters or supercomputers. And so we would like to consider these two computational environments. Okay, from now, I'd like to explain how the frontier star, which is a nonlinear finite element structure analysis program, is added on to freecad, or our recent example of this integrated environment. So this slide shows how to install frontier star into the freecad. So we install freecad 0.90 or later, and selecting tools to activate add-on manager, and select the FEM frontier star and click install selections, and restart freecad after the installation. So once the installation is done successfully, you can see the add-on workbench named FEM frontier star here. Okay, so and this slide shows how to use. Actually, we in freecad finite element structural analysis program workbench called FEM workbench is already included. So we may have some help by over the FEM workbench. So at the pre-processing stage, we will create the 3D models using freecad, using part design workbench. And afterwards, we go to the FEM workbench, where we will generate the finite element mesh or assign the material constant and the boundary condition settings. Then we activate the switch to the front ISTA module here. Then these finite element input data is converted to the front ISTA input file, and a binary executable of front ISTA is activated by double clicking the button. Okay, and once the parallel computing of front ISTA is executed, maybe at the stage of post-processing, you can see the results by using the FEM workbench functions, or by outputting the VDK file, and then we can use the open source post-processing tool like the Paraview. Okay. So I will skip this small comment. And also, when we just use a local environment, a CAD model mesh creation, file input, input file export, and loading displays results. They are normally done at the local working directory, but if you are going to run the finite element parallel computation at the remote side, then some related files are sent. And after the structural analysis, output result is sent back, and we can see the result by using the post-processing tools. Okay. And so we have tested some structural analysis case. Even though the front ISTA includes various functions, not only in the linear elastic problems, but in this case study, we just assumed the static linear analysis to compare the computational time or speed up of the parallel processing between the front ISTA and the Calculix. And we have set up these 4 models, and for each model, we have prepared small, medium, large models. And so you can see the difference of these two finite element programs. Calculix is the finite element solver included in the FEM workbench, and the front ISTA is ours. Okay, and so due to the limitation of time, we just look at the Spring model result. So, and for the largest case, Calculix computational result is these 2 bars using using the iterative solver, equation solvers, and the direct solvers. And these right-hand side 2 bars are the result of the front ISTA for the iterative solver and the direct solvers. Okay. So we have learned very much thing throughout the FreeCAD add-on development. So we have learned these 2 points. The forum is very helpful. Also, we have learned that the creation and the publishing the manuals on MediaWiki, etc. Okay. So finally, I'd like to conclude my talk. We have tried to establish the one through computational environment using freecad and FrontIStar. And sorry. And still, we have many things to do to incorporate the various nonlinear analysis functions of FrontIStar into the FreeCAD. But we have found that it's very, very helpful and useful tools. And this is the last page. Maybe you can find the various side how to obtain the FrontIStar, or you can see some video of using FreeCAD with FrontIStar. Also about the FrontIStar, you can find the tutorial video here. So please look at these slides later on. So now I'd like to close my talk. Thank you very much. And I'd like to show my great thanks for Barnu to help me or give me a chance to talk.
Thank you so much, Hiroshi. So you are, I have removed you from the stream. So to all the viewers from today, this marks the end of our presentations for the day, for the first day of the FreeCAD and FreeCAE Users Conference. If you would like to engage with Hiroshi, you are welcome to join the Sessions tab on the right of your screen. You are able to access the Q&A session. So if Hiroshi is able to go to that and you guys want to engage with him, you are welcome to do that. If not, this is the end of the road for today. On behalf of the University of Pretoria, our sponsors, the Royal Academy of Engineering, the Lloyds Register Foundation, as well as the Engineering X, I would like to thank you so much for attending the first day. Tomorrow we will be bright and early at 12 o'clock, GMT 02 South African time, where we will begin with the next round of presentations as well as engagements. Big thank you to all of the speakers who showed up today. Thank you so much for making the time to have the presentations, making the time to engage with the wonderful FreeCAD community, both veterans as well as new users. But on that note, I'd like to thank you all for attending, and I shall see you tomorrow. Thank you.